Greetings and welcome to another ReMBlock screencast. In this screencast we're going to start looking at how YAWL manages and works with memory. So let's take a look at this smart contract that I've got here called YAWL memory, which we'll be able to use to play around with some of the basic parts of working with memory in YAWL. Now before we begin though, I just want to explain the reasons why we need memory when we're working with Solidity smart contracts. I've listed them here, the key points that we need memory for. And it's really just for returning values, for setting the arguments, for getting values from external calls, to be able to revert with a specific string, for logging or emitting logs, for deploying new contracts, and to use the Gecko 256 function. Now please note that with Solidity there is no garbage collection for memory, and the organization of memory is basically it's arranged in 32-byte increments or sequences, and there's only 4 instructions that you need to really know about with memory management in YAWL, and that is mload, mstore, mstore8 and msize. So we're going to look at these functions as we go forward, and in this screencast we're going to look at mstore and mstore8 as we can see in these 2 examples. Now if you want to dive in further, you can look at the Solidity docs and specifically go under YAWL, and you'll see all the instructions and explanations of the different variables and functions that you can call within YAWL. And obviously the mstore and mstore8 that we're going to look at right now are documented here as well. So firstly, let's start off with the mstore example. And what I'm doing in this example here is I'm using mstore, and the mstore function takes the location that you want to start saving the data in memory from. So in this case, location 0. And I want to save this 32-byte word here, which is basically all ones in binary. Okay, so 0xf is basically all ones in binary. It's the largest UNT256 that you can store, and it's basically I'm just doing this so that we can see exactly where this looks like and how it's stored in memory. And then I'm going to reset it so it goes back to 0 at the same slot, but then I'm going to store the same value, basically all ones, but I'm going to store it at memory slot 1, just to show you how the offset works with mstore. And we're going to do this by basically calling the function, which is down here, mstore example, and then debugging it so that we can see here in Remix debugger how this looks. So if you haven't used this before, you've got a bunch of different things you can look at here, like the stack, the call stack, the call data, and so on. And what we're interested in, of course, is memory. So if we first of all just click copy, I've got a notepad here open, and we can get rid of this extra question mark to make it clearer. And you can see here that the memory starts off, as I mentioned earlier, that it's in 32-byte increments, and we got address 0 and address 20. This is obviously in hex, this is 32, so this is the first word, which would be from 0 to 1F, and then from 20 to 3F, and so on. And these are 32-byte increments. Now we can take a look at that by just loading this into, say, a node console and taking the length of this. And you can see the length is 64. Well, it's hex, so we divide it by 2, and so therefore it's 32 bytes. So that's the state of the memory. Now you'll notice here it's zeros, zeros, and then an 80. Now this 80 here at this position of 0x40 is the free memory pointer, which we're going to be diving into later. So if we step through these calls up to the mstore here, the first mstore, we can see what happens in the memory. So let's step through that until we get to the mstore. And there, the mstore has been executed, and you can see, as expected, all of these Fs are now stored in the 0th slot or the 0th address position in memory. So we've got this here, all these F's stored here. Ignore these question marks, as it's just extra stuff from Remix. But you can see that's what's happened. Now, if we go back to the instruction set and continue to loop through the instructions here, or work through the instructions, we get to the next mstore, which will clear out the memory. So keep an eye on the memory slot 1 there. And you can see there it's now cleared out. So it's back to zeros again. So the next instruction is mstore at position 1. So an offset of 1 byte, where we want to put these Fs. So what's going to happen is we'll see that the first byte will remain as 0, that's these 2 zeros here, and then the rest will be filled with Fs, and including this part here, because it's basically shifted over by 8 bits. So let's have a look at that. So let's just continue to call this, and then once we get to the mstore, you'll see that it exactly is as I mentioned. We've got all the Fs here with leading 2 zeros because the first byte is remained unchanged, because we said start from position 1. So start from the first, after the first byte here. So that's why we have 0, 0, then all these Fs, and then we have FF in this position here. So I just wanted to show you that that's how basically mstore works and how the positioning works in this function. So let's stop debugging that and take a look at the mstore8 example down here. If we go into the functions here and we call mstore8, and again we don't get any output or anything directly in the terminal here, but we can debug this and take a look at what happens. Now, the purpose of this exercise is really just to show you the difference between mstore8 and mstore. And again, in the documentation, you can see that mstore8 only modifies a single byte. So it will only modify the 0x00 or 0xFF part of the storage. So mstore8 at 0th address slot there will add 7 to that position in memory. So if we just collapse the stacks here and look at this, you see it's all zeros right now, but what will happen after this instruction is this will change to 0, 7. So let's go back here and execute the calls until we get to the mstore8, and you can see here that that's what we get. We get the 0, 7 right at the very beginning in slot or position 0, and it's just written the single byte. Now the next line is an mstore, and remember mstore always works with 32 byte words. So what that's going to do is it's going to store the 7 at address 0 in memory, and because it's working with 32 bytes, it's going to basically lead the 7 with zeros, and it will clear out this 7 here. So let's take a look at that. As we move forward, it's going to call mstore, and then there you can see the memory ends up being all zeros with the 7 at the end, because the mstore function was called and it added that data to the 0 address in memory. So that's a quick introduction to memory in Yule, and we looked at the mstore and mstore8 functions.